So no seminar is complete these days without touching some machine learning, I guess. So I'm going to do my share of getting you exposed to a little bit of machine learning. But it's going to be staying on one particular corner of machine learning, which some people call graph neural networks, some people call geometric learning, graph representation learning, lots of different names. The main idea in graph learning is use the connectedness of the data to learn from your neighbors, right? It's some sort of what they call as an inductive bias. When you're looking at regular data, you consider there's no structure, everything is connected to each other, whereas in a geometry, in a graph, you're kind of given some sort of structure, and you can use that to learn better and faster. But what actually struck me more is, this is the code from a really nice manuscript. They're going to convert this to a book, I think, by Bronstein et al. But I have also observed this before reading this, that graph neural networks are actually, can be thought about generalizations. When you look at convolutional operations in convolutional neural networks, it's some sort of look at your neighbors, but your neighbors are regularly defined on a grid, on an image. All your nearest neighbors, if you define 3x3 convolution as your 3-point neighbors. It's your nearest neighbors. If you define a bigger convolution window, that's your 2-hop neighbors. So it is some sort of a graph as well, except it's a regular graph. You don't need to specify connectivity in adjacency matrix. You know it by definition, so to speak. And a very commonly used thing like transformers in natural language processing is actually, you can think of it as a graph neural network with fully connected structure, right? And so on. So it's just that GNNs are almost the most general thing. And every single other variant of deep learning machine, you can think of this as specialized versions. Well, obviously, that's not really helpful, right? Because finding that something is more general, if it's not faster to compute on that, it usually results the opposite direction, right? If it's too general, it's more expensive to compute. Yeah, hypergraphs are generalizations of graphs, but you can't prove even 1% of what you can prove with graphs and hypergraphs, so something like that. But luckily, graph neural networks are sufficiently constrained to be useful. So you'll see papers like this, the powerful antibiotics discovered using AI. But you have to kind of read the paper a little bit in detail to figure out this is actually a graph neural network, what they consider as the architecture. This was, I think, a Cell paper. And this is a slightly more controversial result because of a recent discussion that came out of it. Google researchers actually started using graph reinforcement learning for placing the wires on their chips, designing the chips in their TPUs. And this is not only became a Nature paper. Now, you should imagine how rare it is to have a pure computer science paper in Nature, right? So this is that kind of an accomplishment. But not only that, they actually started using this process while building their TPUs in the latest generation. So it's not just a research paper, it's actually running. So there is clearly good use cases of this technology that are coming up. And longer list of these things that some of my colleagues are working on. They work on applying graph neural networks in power grid, particle physics, where they try to track how the particle is moved after they created this big collision, whatnot, because it's really hard to actually reconstruct these tracks. Transportation problems are solved, protein problems, materials discovery. That's the harder problem, the inverse thing of, you give me a property, I give you a molecule that will have that property. That's the inverse design. And lots of work, really hard problem. But somewhere in there, graph neural networks are used as subroutines in these. So you can do a couple of different things on this. You can classify graphs with graph neural networks. You can classify edges, or you can classify vertices on a graph. And I'll generally constrain my talk in node classification. But the important thing to emphasize here is these are computationally intensive to train, like every machine learning algorithm. But there is an added complexity. They're irregular because of the sparsity. Graphs are sparse, so instead of doing your dense matrix computations, now you have to do lots of sparse matrix computations. And there doesn't seem to be a way around it. And that makes them significantly more challenging and expensive for large-scale computations. And this is just a pictorial way of describing what I just said. Once you compute the latent representation of all the nodes and the edges in your graph using your graph neural network and your training data set, then you can use this to classify the nodes, classify whole graph by combining all the latent representations of all the nodes and edges, or just do the link prediction, which also is very useful too. Link prediction, many applications I work on, is actually the #1 use case. So how many of you actually have looked at convolutional neural networks at all? Okay, so this is going to be fun. Maybe that contrast is not that useful, but here's what I'm going to explain why this is actually significantly harder problem in many cases. So when someone trains convolutional neural networks, they usually do it on images or text, and every single input is kind of independent from each other. You're given a couple million pictures, some ImageNet data set, some other data set, and image A is essentially an independent sample from image B. So you can just say, I'm going to train on image 1, update my weights, the neural network parameters, and then move on, train on image 2. And for performance, you can increase the number of images you train at once, instead of using one, which would be what people call pure stochastic gradient descent. I mean, optimization people will kill me for calling it that way, but, and now you can say mini-batch gradient descent, which is you train on 256 images, 1,000 images. After that, it starts having convergence issues. But the independentness allows you to decouple this problem to however many samples at a time you want. It keeps the memory cost low, and it somehow helps the convergence because it escapes local minima better. Now, move to graphs. Here's the problem. Well, my samples are nodes if I'm doing node classification. I have one big graph, like the protein network maybe I just showed you, which has 300 million vertices and a couple billion edges. Okay? It's protein similarity network. I can't just consider these nodes as independent entities because my learning process will learn from its neighbors. And after second layer, it's going to learn from neighbors of neighbors. So I can't just say, you learn only on these 2 vertices to the system because once it starts training, it's going to want to look at the neighbors and neighbors of neighbors, and eventually it will touch essentially everybody. Like if your initial starting batch is these black nodes here in the center, even with a fairly regular graph, this is not a small word graph, this is a fairly regular graph, you'll see that after a couple of steps, it's touching a much bigger portion of the graph. And if you heard this phrase called 6 degrees of separation, in a lot of small word graphs, with a neural network of 6 layers, you're going to have to touch every single other vertex. So that makes sampling-based learning on these things really hard. So I'm going to, for the purposes of this talk, take a shortcut and say we're going to train on the whole word graph. What that means is a full graph training. So instead of taking a small piece and trying to train on this, we're going to use the whole graph all at once. There's pros and cons on this method, but this seems to be actually faster because it doesn't do redundantly touching the same things over and over again, even though its convergence is a little slower nowadays. And so I think I gave you enough motivation to say why we're not doing sampling, but this is mostly was designed for people who kind of are familiar with convolutional neural networks, and I'm contrasting with that, but maybe I didn't need to do that here, it turns out. So here's another nicer picture. That's what's going on. But every vertex, like now let's say the focus here is 1, every vertex learns from its L-hop neighbors, assuming the network is at least L deep. Okay, so that's like at every stage in the neural network, every layer, I learn from one hop away neighbors. So I get somebody else's feature vector. It can be randomly initialized, but it's usually some information that's there, right? For proteins, it's very obvious. I can just take my sequence and run it to a compression scheme and use it as features. Or in a social network, I can just use the knowledge I have about that person's, political beliefs, their purchasing history, their age, their gender, whatever they provided me as my initial network, and it's going to get propagated up and up. And then this thing is going to update its feature vector based on the information it gets from neighbors and from itself, and change the parameters based on the supervision data, training data, and so on. And this is just the same pictures in neural network layer sense, right? So that's what's going on. And this is going to happen one way for forward propagation, for prediction and figuring out the result. And then the backward propagation, essentially the equations will be reversed from the other direction to update parameters. And these dimensions might be different at each layer. And that's very typical in neural networks. You sometimes want to create a bottleneck in the middle so that it doesn't overfit. But that's like a little extra information that's not relevant. The important thing I want to emphasize at this point in the slides is these are bigger than the input usually. Even if you're given a billion node graph and you think you can fit it in your processor, it's actually a worse problem because in order to backpropagate later, I need to keep track of all these embeddings at every single layer for each node. So my memory consumption is not just the graph size. My memory consumption is n is the number of vertices, L is the number of layers in the neural network, F is the average dimension of the features. So, you can take some numbers and see that you would need a terabyte just for 100 million graph, and we already talked about bigger graphs, deeper networks, and so on. So this quickly requires distributed memory, not only for storage, but because it's so expensive. So how do you train with that? You can look at this as for each epoch. An epoch is this thing that you use in machine learning, which is a single pass over the data. Because of the stochasticity, people pass over the data many, many times until convergence. So you can do usually, 50 epochs to train. Repeated passes over the data. So that's the outer loop. The inner loop is for each layer on the network, you propagate your embedding thing, and there's this mixing matrix that mixes between features that is shared across all the nodes. And that's a really small, dense matrix of F by F. And these two F's might be different, as I showed you in the previous figure. Here it's 2, here it's 4, but that's okay. Just calling them F is easier. And then the backpropagation, you see that it's almost like the operations are kind of reversed. And what do we see here? Here we see a sparse matrix that represents the graph times a tall, skinny, dense matrix representing features of the nodes and that tiny little dense matrix. And here the adjacency matrix is no longer transposed. And instead of the features, we have their first order derivatives. And then there's another way of computing also the updates to the weights. So the main workhorse, whenever F is small, which it is the sparse matrix, tall skinny matrix multiply, which is this figure, right? So this is what represents the graph. This is all the embeddings so far in layer L-1. This is the learnable matrix. And then once I update this, I get essentially embeddings for the next layer, alt layer. And I keep doing this for forward iteration, and I do a similar computation on the backward backpropagation. And naturally, the cost of this first multiplication is significantly larger than the cost of the one with the dense matrix, just because this is 200 by 500 as opposed to hundreds of millions here. Okay? So my next pattern that I care for that reason is sparse matrix times tall skinny dense matrix. Sparse matrix is the graph, tall skinny dense matrix is the features. This occurs in graph neural networks, graph embeddings. It actually occurs in eigenvector computations these days. If computing eigenvectors iteratively, the textbook example is Lanczos algorithm, but if it's a symmetric system, or Arnold if it's not symmetric. But nowadays, because of the way the computer architectures have evolved to have more what people call is the more flops per byte, methods that work on multiple vectors at a time are more popular, like LOPCG is locally optimized block conjugate gradient descent. I think would solve your eigensystem faster than Arnoldi. So for that reason, this is also a primitive that occurs outside graph neural networks. And it occurs in non-negative matrix factorization algorithms, so on, which I didn't list here. So that's basically the operation. You can just see the motivation here, just focusing on one column or one vertex. So what's going on is just V6 is gathering the feature vectors of its neighbors, is essentially just a multiplication of this sparse row with this dense matrix, tall skinny dense matrix. And you see the pattern here. It's the same as what we talked about. When I want to gather something from my neighbors, it's always sparse matrix times something. And that something depends on whether it is gathering a long feature vector or whether it's gathering some sparse thing, which would make it sparse vector and so on. So that's why these same primitives come over and over again. And I'm just going to go 2 slides before. Reordering seems more makes sense. And when we implement these things, we actually use some technology that I haven't talked a lot, which is communication avoiding algorithms. There's, how many of you have heard that term at all? Oh yeah, that's more popular here, good. So this has been, I don't know how, the name I think is due to my colleague Jim Demel, but the kind of algorithms that communication avoiding has a longer history, I think. When I was a grad student, I was kind of shocked, like, what does it mean to have a 3-dimensional matrix multiply algorithm? 3-dimensional parallel matrix multiply. The whole matrix is 2-dimensional, right? And once you read that, it makes a lot of sense, because the computational cube, the work you're doing is 3-dimensional and cube work, and you're just dividing the work to processors. So you're trading, but that creates extra memory issues, because once you divide all 3 dimensions, then the intermediate storage of the that you need to keep track of is asymptotically larger than your input and the output size. So, but they reduce communication. So that's the simplest way people explain it. They trade extra memory consumption to lower the communication costs. And generally, that's kind of the general definition of communication avoiding algorithms. And we use those algorithms here. There's these algorithms, what we call is 1.5D algorithms. There's a little obscure beast, and I'm not going to spend too much time, but think of them as dividing the sparse matrix in 2-dimensional form and dividing the dense matrix in 1-dimensional form. And intermediate level, there is some replication. So the storage consumption temporarily goes up by a factor of C. But you can see when you do that, you get much faster results. C equals 1 is a pure 1-dimensional algorithm. C equals 4 is, becoming more and more 1.5-dimensional. And you can, debate me that the name is obscure, and I won't say anything against it. But we were able to scale some of the challenging problems reasonably well. This is a really hard problem to scale. So these plots don't look like linears that you would find a lot of parallel computing papers, but at least the reviewers appreciated the challenge, and it's going to get better. The architecture is also a little bit obscure machine. This is run on a summit, which is very under-provisioned for communication. So are we done? Can we just do sparse matrix times dense matrix and solve graph learning problems, graph representation learning problems completely? It turns out it's not yes. There's a lot more research to be done. And some of it is going to go back to what I started telling in the beginning of the talk, which is semi-rings. So a colleague of mine, Stephanie Jegalka in MIT, they have been doing this really fascinating work that is way beyond my understanding to develop, but at least I can appreciate what they're doing, is if you want to solve a certain problem, like let's say a shortest path, you want your architectures to match the computation, more or less. So that's kind of the summary. And what they have done is basically, let's say I want to solve compute shortest paths using graph neural networks. But I only do multiplies and adds like in the standard floating point sense within my network and nothing else. It gets much harder for the network to learn this phenomena. And sometimes it doesn't converge to anything useful. But it says if knowing that the main function in shortest paths is this relaxation operation, we all do, right? We look at, if I can come there from, if I go to V through intermediate hop U, then I would use the distance to U plus the weight of the edge from U to V. And if that is smaller than the distance I know to V, I'll take that as my new distance to V, right? This is the same operation that every shortest path algorithm does. So what they do is like, okay, seems like minimum and plus is the algebra here, like in the semi-ring sense, like what we use when we do shortest paths in the language of linear algebra. That's what we do. We overload the additions with minimum and overload the multiplications with addition. So that's what they do in their graph neural network and use this minimum operation for combining and addition for the aggregations. And then MLP, this perceptron, multi-layer perceptron, only has to learn linear steps because all the nonlinearity it has to learn, I already encoded in my algebra. And it gets into much better results I'm going to show in the next slide, especially for what's considered as extrapolation, meaning you're asking the network to solve a shortest path problem on an input that it doesn't train on, which seems to be the only useful case. Otherwise, you know the result. And so for example, this is, if you just use the standard sum for polling, the error you get is shown in the gray one. But if you use max-min kind of stuff for polling, which is this kind of readout of the neural network, you can get zero error. So it's a fascinating paper. There's a lot of good theory supporting that too. So essentially all it's saying is the graph representation learning libraries should support arbitrary operations, arbitrary semi-ring computations. GraphBLAS API does that, but how many, let's say, GPU implementations that are out there that people use, because people kind of end up using NVIDIA, whatever NVIDIA provides them for deep learning. And it turns out actually things are moving in the right direction too. NVIDIA's cuSparse, which is the #1 thing people use as a backend for their machine learning libraries for sparse computations, just like a couple months ago got this new function called cuSparse SPMM, which is the acronym for sparse matrix times tall skinny dense matrix, op. And the key point is the op here, meaning that you can send your own operator for additions and multiplications. And that seems to be telling that people are, following through with this theory, and they're supporting arbitrary user-defined operations, even as a vendor-supplied library. So, but we're not done not just for semi-rings. We're not done because graph neural networks do more than convolutions. So far, all I talked to you about is the operation called graph convolution, meaning look at your neighbors and combine their features in some way. But what is the right way to learn? Do I have weights in my edges? The original graph convolution doesn't use weights. It just combines every single neighbors in features in the same way. It treats every single feature, every single neighbor indiscriminately the same way. I think after you talk 2 hours, it kind of gets hard. There is a higher level, I would call it higher levels, that is a higher power of learning neural network, graph neural network called graph attention networks. So there, instead of just treating every single neighbor the same, you look at how your features are similar to that vertex or how different. And that is learnable in the sense that you learn what part of it you pay attention to, right? It might be that some of your neighbors are different than your others. Like you have 100 neighbors, 80% of them just are pretty similar to you. So they don't carry too much weight. But there is this 20% that seem to be telling you more. And as you train and you update your scores based on those 20%, you see that you're getting more gains in your accuracy. And the neural network will learn that after a couple of epochs and start paying more attention, so-called, to those neighbors. And that's the name attention comes from. So how can I compute attention? Meaning which neighbors I should pay more focus on, give more weight when I'm combining my neighbor's function is simply, is this operation called sampled, people call this sampled dense matrix multiply, and I'm not going to change that name, of course, because they already have it. This is the mask matrix multiply, except the matrices are dense because these are the feature vectors and it's transpose. So all I'm doing is inner products between them in the simple case. Of course, this is not always inner product, but the simplest version is inner product. I took my features and my neighbor's features, I do an inner product, and I'll figure out how much attention I should pay. And I'll change that function for more sophisticated networks. But this is the computation and data access pattern will stay the same. And I don't want to compute inner products between all the nodes because I only care about those that has an edge between them because those are the only weights I can update. So this is from the perspective of vertex 1, I want to figure out how much weight I should give to all my neighbors. And the way I do it is inner products of my features to my neighbor's features. And that's going to become, for each non-zero in the graph, do the inner product. So sampled dense matrix product. But again, it's a masked dense matrix product too, depending on who you ask. And that seems to be that became one of the two very important machine learning primitives for sparse learning. So one of them was SPMM, I showed you in graph neural networks, and the other one is now the sampled dense matrix product. Now, my student, Vivek, started looking at this problem, sampled dense matrix, and he was going to write a paper about it, new algorithms, because there weren't any distributed memory algorithms for this. Instead, he came up with a different paper, which is always more exciting, because you have a new discovery. If you know exactly what's going to come out of the paper, then that's not that exciting. So he just basically showed this is the same thing as what we already know, which is what I talk, sparse matrix times tall, skinny, dense matrix. Sampled dense matrix product is computationally equivalent. Why? Because in both cases, you're looking at a sparse matrix and saying, for each non-zero in the sparse matrix, so this is ij in S, for each non-zero in the sparse matrix, compute the inner product between a dense matrix and, no, sorry, not combine. For each non-zero in the sparse matrix, for the SPMM case, you touch one row of the dense matrix and you write one row of the output matrix. In the sampled dense matrix product, again, for each non-zero, you touch one row of the dense matrix and another row of the dense matrix. So you touch two rows of dense matrices. The difference here is in one of them, one of the dense matrices is in the output. In the other one, both of them are in the inputs. So that seems like they're pretty close, but better yet, Vivek gives a direct mechanical translation from any algorithm that computes one of them to create an algorithm that computes the other one with the same communication bounds. So they can be arbitrarily complex algorithms. They can be this communication avoiding algorithm, 2.5D, that does sparse matrix times tall, skinny, dense matrix that we already developed. And then by some simple mechanical transformation, that you get an algorithm with the same optimality conditions and same bounds for the sampled dense matrix product. And that's really the simple mechanical transformation. However, he actually, of course, didn't stop there and noticed that this is actually not his discovery. one of my colleagues at Indiana University discovered that these two operations almost always come after each other. Now you can imagine it in graph neural networks. That's obvious because what do? Well, when I need to compute attention, first I figure out these weights, and then I do a weighted convolution, which is SPMM. So I first do this, and then I do SPMM. I first do this, and I do an SPMM. So they keep following each other. And this operation, sample dense matrix product, almost never happens in isolation. The other one kind of happens in isolation sometimes. So he came up with these few algorithms for fused MM, for distributed memory, that has a bunch of optimizations that avoid redistributing intermediate values. So you can either do local kernel fusion or replication reuse, because these communication avoiding algorithms do replication, again, to reduce communication. So you don't need to replicate in the middle of the computation. These are mutually exclusive optimizations, so you can't apply both. But in the end, the similar results. Good stuff. Which algorithm to use is very complex decision, it turns out, because it depends on the ratio between the number of non-zeros in the sparse matrix to the number of non-zeros in the dense matrix. And based on that, you have different optimal replication factors. And then it makes creating scaling plots really complicated, so I'm not going to talk about them. And that ends my machine learning with graphs section. So sparse matrices are useful, but it turns out the number one primitive we use there is sparse matrix times tall skinny dense matrix, or using the sparse matrix as mask, tall skinny dense matrices are inner product. It's with themselves. There is a different area I want to emphasize that I didn't cover, which is when the sparsity is not in the input. In this case, the sparsity comes from the input of the graph. There is a different area of sparse machine learning where people kind of induce sparsity, right? Because you can sparsify the gradients. You don't need every single gradient. And then that creates a little bit of sparsity as well, except it's really hard to take advantage of that, because once you throw away more than 90% of your gradients, it starts hurting accuracy. Well, if your sparse matrix is only 90% sparse, it might seem like, oh, there is a factor of 10 to be gained, but there isn't, because dense codes are so fast. They are so well optimized, and they have this ability to reorder themselves and take advantage of the architectures, that a 10% dense matrix, you better run dense code almost. So I call it the twilight zone of sparsity. It's not clear if you're going to get performance there or not. You have to work really hard or develop new algorithms. But if you want new research area, that might be actually a wonderful place, because it's very under-invested and not well harvested. It probably has a lot of money too, by the way. Why do I say that? Because seems to be some of the leading researchers in that area I've seen actually started his own company. So there might be some money there. So I'm looking at this plot figure that I'm going to talk about, except that it doesn't actually project well. But that's okay. I actually don't know what these darker rectangles here are, because that's what happens when the operating systems are different. Even though this is the same PowerPoint, one of them is for Mac, one of them is for Windows, and here we are. But ignore the dark rectangle. So I talked a lot about this signature, but you can see how many different exact functions this signature maps to. This is the signature of graph plus MXM, matrix times matrix. In itself, it hides many algorithms I talked today. There can be a mask, or there can be no mask. The inputs might be sparse, both. One of them might be sparse, one of them might be dense. Both of them might be dense. It only makes sense if there is a mask, of course. Otherwise, it will be just typical DGEM. So you create a lot of these variants, which are sparse matrix, matrix multiply, SPGEM, when A and B are both sparse. Masked SPGEM, where same as before, except there is also a sparse mask. SPMM, which is just what we talked about, where B and C are tall, skinny. Sample dense matrix product, where inputs are dense, but there is a sparse mask, which obviously creates a sparse output. And then the SPME and SPM-SPV, which is vector cases, are just degenerate cases of the other two, where B and C has only one column, right? So this actually would map to 6 different functions under the covers. But one thing that's good and bad about GraphBLAS interface, the way it's implemented, is you don't need to know, because this can change. I can start with a dense vector, as in the case of maximal independence set computation. After 2 iterations, it's going to become a sparse vector. I don't want to know as the algorithm designer. I just want to write the code in an interface that doesn't talk about sparsity of matrices and vectors, so that when it executes, if it's sparse enough, the library will call a different function internally, because that's the correct way to do it. I will never perfectly predict when it's going to cross a certain threshold. The library implementer should be able to look at it. Oh yeah, it's 90% sparse. I'm going to switch to the other function. And the signature should stay. The declaration of the object should stay the same. And that's what we try to strive, so that the algorithm designers don't care about the cutoffs of sparsity. So I am at a place that I'm just going to talk about a few algorithms and conclude. This is actually the nerdiest part for me. So please raise your hand if I go too nerdy. The original algorithm to compute this sparse matrix multiply is from 1978 due to Fred Gustafsson, who was at IBM for a long time. If you ever used an IBM computer, the chances are you used his software at some point. He wrote the equivalent of matrix kernel library for IBM. It was called ESSL, but he retired a decade ago, I think. And his algorithm still drives every single algorithm. So the way you multiply 2 sparse matrices is you take a column of the second matrix, which tells you what columns of A you should merge and combine, and you form the same column of the output that way. Now, the way he described it, you would use a dense vector to accumulate these contributions. Why? Because he's thinking in terms of serial computing. Back in 1978, a dense matrix gives you random access to locations. So I'm just going to go over this, write it here, go over that, add it to this. But you also need a couple more extra things. One thing you need is you need a list of all the non-zeros, because you don't want to go over the whole dense matrix to figure out which ones are 0. That will take order and time. You just want to be able to output this dense matrix in time proportional to the number of non-zeros in it. So he needs a list of what is inserted, and he needs a Boolean flag to tell whether an entry has been updated or not. And that only matters for numerical cancellations. Otherwise, you can just check if it's 0 or not, right? And there are techniques to avoid that. So that's called Sparse Accumulator, the way it was called in MATLAB. When Gilbert, Moeller, and Schreiber wrote the original sparse matrix backend for MATLAB. The trouble with this algorithm, when you try to do parallel computing in multi-threaded environments, like your laptop or anything with more than one core, is these dense vectors, they need to be kept for each thread, and they start running out of cache collectively, right? So that seems to be a problem. When I have 64 threads in my real computer, I can't really afford 64 of these huge dense vectors for large matrices. So we come up with another garbled figure, heap size. You can use a priority queue, what I call a heap, to merge these columns. And then you'll just go over, the heap should only be as big as the number of columns you're trying to merge. That's great, except that it has this extra logarithmic factor and seems to be only super fast with sparse inputs, really sparse inputs, and not so great with things what I call as high compression ratio, and I'll define compression ratio in a slide. So I had an intern from Japan, Yusuke Nagasaka, and he had an algorithm for GPUs for doing this operation. merging phase. So we wanted to use that and see if it can be a better accumulator. So instead of a heap, instead of a dense vector, we're going to use a small hash table. Can we do that? And will it work? It turns out it works beautifully. So this is, the higher is better. And the compression ratio is on the x-axis. So if you want to keep your input sorted, output sorted, it's kind of this line that sees the green line is pretty good on the top with the hash algorithm. And if you you don't care about your output to be sorted, then I think using MKL, Intel's MKL was faster. At least one variant of it was faster for large scale, but hash is pretty good for a lot of ranges. It's good for low compression region and not so horrible in the high compression region. So what is compression? It's really the number of intermediate products that contribute to the output. So in a dense matrix multiply code, it's n. For each non-zero in the output, you do exactly n scalar products and add those together. In sparse case, it doesn't usually go over 100 at all. Sometimes there's only one intermediate Aij, Bjk tuple contributing to an output, but that's normal. So, there's many, many libraries. I actually like this slide because when I started talking about sparse matrix multiply, there were 0 GPU codes. Now I have to update this slide every year. This is just a snapshot of 2018, and since then, we have more than double the number of codes. Each one of them is better than the previous ones. Otherwise, they wouldn't be published, right? I think right now the fastest thing is something called an ACSP jam. So that makes me happy. I haven't developed a single one of these things, but I'm really happy to see them exist. But what part of it that got me excited is this mask matrix multiply. I talked to you about why I want to use masks in the beginning of the talk, triangle counting, or when I do breadth first search, when I don't want to revisit the vertices. So can I do masked SPGEM efficiently with minimal effort? So we went to this work, again, a collaboration with a summer student, where this is a too complex of a figure, but really this is the mask matrix multiply. The whole idea is, I talked to you about a sparse accumulator, which had 2 states, which said whether the non-zero has been contributed or not. Well, we said if there is a mask, we can just create 3 states, which is, one is whether the non-zero has been contributed to the output, whether it's allowed, or whether, so those are the 3 states. It's either not allowed, contributed, or allowed but not contributed yet. So instead of a Boolean flag, you have an array that can take 3 different states, 0, 1, -1. And then this way, as soon as you see a scalar Aij, Bjk happening, you can check whether it makes sense to do it in the first place. And if it's not, then you will skip it because it's not allowed. And you can very efficiently set non-zeros to be allowed and set them to be basically clear it for the next column. And that algorithm was our first algorithm to try. And we tried successively more complicated algorithms. And it turned out none of them beat this one. The simple algorithm was so good that all other algorithms we developed was essentially useless. But that's a good and bad thing. I don't know. It made the paper harder to get accepted. But at least it showed. So what is this plot saying? It's this is the fraction of test cases. So we have lots of test cases. You can read more of them in the papers. And this is the runtime relative to the best. So if you're a straight line here, meaning you're the fastest code in every single instance, right? And so for example, when we're running between centrality with this code, this what we call is the MSA, the masked sparse accumulator I just showed you, is faster than anything else out there for every single case. So nothing else needs to be run. All for the close is 70% of the cases is the fastest. In the worst case, it's 60% slower. Here, 80% of the cases, it's the fastest. In the worst case, it's less than 2x slower. So it kind of became pretty obvious what to run in some sense. There is still a little bit of you can do for this 20%, a different algorithm you can choose. But the gains you're going to have is limited to less than 2x. So that was really nice, or not, depending on your perspective. And you know, my group has, of course, done more research on these primitives. Once you identify them, then you start working on developing algorithms. Like we wanted to do more work on sparse matrix, tall skinny matrix, and we developed, this is kind of, I didn't describe you 1.5D algorithm. It's really like this. 1D decomposition of dense matrices, 2D decomposition of A, which means temporarily, in order to do a multiplication of my piece, if I am the processor that's holding the blue blue submatrix, I need to not only get access to my blue piece of the dense matrix, I also need to get access to the gray pieces from my neighbors, and I also need to create the gray pieces. So temporarily, I am storing more than I need to store for the input and output dense matrices. That's what makes it 1.5D. But the number of stages of the algorithm is lower. That increases the arithmetic intensity. So we studied a lot of things that probably is too late in the conference to talk about, like one-sided communication, remote direct memory access. We do lots of high-performance computing. I'm just going to close this out with some code you actually can develop if you want. So if you want to develop, use sparse matrices for data analytics purposes that I described, or things that I haven't heard about yet, one library I developed initially, and now other people have contributed and became the lead developers since then, is Combinatorial Blast. This is for distributed memory, and it runs on effectively all the supercomputers we tested, has good I/O support, it supports CPUs, GPUs, and since we developed version 1, you can actually compare how much we came. The original CombBlast, for example, is the blue line. Now we're at the red line. This is just for CPUs. And even with so we're like, this is log plot, so this difference is actually significant for optimizations. Not only that, we also have a GPU branch, which is faster than the red line here. So by, again, a factor of, I don't know, 2, 3, something like that. So it's going to run on any high-performance architecture you have. But if you want a single-node GPU stuff, there's GraphBlast, which, again, one of my PhD students have developed. It was published in ACM Transactions of Mathematical Software after a long process, which apparently is typical at Tom's. It does a lot of the optimizations that I talked to you about. And it was faster than all the graph processing libraries out there. Now I want to give a shout out to all the other people that developed GraphBlast-like libraries. Right? The things that I talked to you about, Combinatorial Blast for distributed memory and GraphBlast for GPUs, are actually not compliant to the GraphBlast standard that we wrote, because they're all in C++, and the standard is in C. So we kind of make it look like it, but it's not going to be directly running. Sparsuit library from Texas, I'm going to show you the developer in the next slide, is the first fully conformant and well-optimized library. Tim Davis wrote this thing from Texas A&M, and Tim also wrote the modern version of MATLAB sparse backend. So he's a wizard in sparse code optimization, especially in a single node serial case. In fact, one of my colleagues, Rob Schreiber, who wrote the original MATLAB sparse code, said, "You got to be crazy to compete with Tim in performance, are you?" And that's right. So that's very well optimized code. And there's many other codes that came after that, Python bindings, 2 of which I'm going to emphasize. And there is Julia wrappers around by many different people, actually. And these are continuing to be maintained. And because my colleagues actually give real hands-on tutorials, unlike what I did now, they actually ask you to have your laptops and pre-install software. That makes sure that the code continues to run every time there is a tutorial given. It's not just that, actually. There's a company that uses GraphBlast code of Tim Davis for their database operations. They have a graph databases, Redis. Redis is the name of the company. And I've seen people playing basketball in San Francisco because it's a Bay Area company with the company T-shirts around. I don't know what kind of revenue they make out of that. But so Tim Davis's code is this, Suite Sparse GraphBlast. Suite Sparse is a general name for everything sparsely developed. You might find other things that are relevant for his code. The GraphBlast is just a subset of it, but his more recent thing. And if you want some cool, nerdy things related to music and other things with sparsity, you can check out his website. He kind of maps his matrices to musical notes and creates logos out of that. I don't quite understand what's going on there. But check out his website. He continues to develop. As soon as we update the API, he will actually make it conformant to the API. And the Python version is actually developed by a small company called Graphigeon. I don't know if the pronunciation is correct. And they're also the number one thing we use. It's essentially a good wrapper around Tim Davis's code, right? So my conclusions are that sparse matrix techniques underlie computations in many different fields, like numerical computing, machine learning, graphs, bioinformatics. And the GraphBlast interface seems to have the right flexibility with the masks and semi-rings to be useful for a lot of disparate computations that I described. We do need to have large-scale parallelism for the large-scale problems that mostly where the interesting part of research happens in graphs, bioinformatics, and machine learning in the large-scale space. Otherwise, most of these things are actually easily solvable without abstractions if you didn't care about large-scale performance. And novel data structures and communication avoiding algorithms are the two techniques that seem to work. And we're hoping to apply it to many other problems. And lots of people that helped. Department of Energy mostly funded the work. And the research team is there. Thank you very much for your attention for this long tutorial session. And thank you for inviting me.
Questions?
Everyone wants good beer in the reception, that's why.
There will be good beer after good questions. Sorry.
I'll ask one so you can...
Okay. This is recorded, right?
This goes back a while from what you did, but I was wondering, you were talking about the pruning. So you did some operation, and then it has to be pruned. Mm-hmm. And so you only take a few columns of the matrix at a time.
Yeah.
And I was just wondering, why don't you do the pruning in the semi-ring operation, so instead of doing it afterwards?
Good, very good question. If it is possible, we would do it in the semi-ring. In general, it's not, mostly because the way you decide what to prune is based on all the other neighbors. So it's like I have to compute something, and then I have to figure out, think of it as the norm of the columns of the matrix. I have to figure that out to figure out the threshold. But there are some cases where you can just, based on the scalar, decide. Even then, it's not exactly possible, because in the semi-ring, you're only computing intermediate products of AI, JB, JK. You don't know the other contributions that's going to happen yet. So you can't immediately prune until you finish computing the whole thing. Unless the pruning is a threshold, then after which you can start ignoring it. So that's actually, some of it is very open research. You can kind of create a scheme that will start pruning if it's based on a threshold. And that's a good idea, actually. I might have not thought about it, so thank you, maybe. But a lot of them looks at the neighbors to decide that. So it's not immediately possible based on just a single scalar.
Are there other questions? Adrien, do we have questions from the online participants? No? Please.
Thank you for your lecture. I would like to know if for a finite field, it will be there's a Blast library, for example, that enables to delay the modular reduction we do for these Blast operations. And I would like to know if there's some similar library that will optimize for finite fields.
Yeah, the direct question about finite field is probably no, because we don't even assume the properties of a ring to begin with. Let's forget about the field. So we don't consider algorithms that are based on, not that there are any analogs of it in sparse word, but like based on arithmetic progression of Strassen and the family of them, because we never can assume that we can subtract something. And so the answer to finite fields is we assume as little as possible, nothing beyond the semi-ring stuff. For delaying computation in general, I can give you an answer that the Graph Blast API that I didn't talk is actually has an, do we call it an asynchronous non-blocking mode, which is you write your whole function, program, it might include 20 different matrix, vector, matrix operations. And the compiler or the library can say, I'm just going to delay the computation of many things until someone wants the readout, and then can go back and see which parts of it I shouldn't have computed because they're getting filtered out somewhere anyway. And that's possible, and Tim Davis, the implementer of this library, actually uses this thing. So when you try to insert a non-zero, he will never insert it in his data structure. He'll just keep it. He calls them the pending tuples. And when you delete something, even if it's not an intentional delete, even if it's like a deletion that happens as a byproduct of your matrix vector operation, matrix operation, he's just going to mark them as zombies because it's expensive to alter the data structure. So he's just going to postpone them until whenever he feels convenient to change the data structure. So in some sense, maybe I'm answering two distinct questions. You asked one question. Finite fields, we don't do any extra optimizations, but for delaying computation and lazy evaluation, Graph Blast API and Tim Davis's implementation support delaying updates and delaying anything until the readout. Hopefully that's somewhat satisfactory.
Yeah.
Other questions? Okay, I have two questions. One easy, and one maybe less easy. Okay, so some years ago, there was a popular topic about sparse matrices, which was for the multiplication of a sparse matrix by a dense vector, let's say in an iterative method where you multiply that matrix many times by a dense vector. And that was the rearrangement of that matrix in order to minimize cache misses. Mm-hmm. You have not mentioned that much. Maybe this is a problem which is well solved and you have existing code doing that. That's
a good area of research that I think still people do it. A lot of the cool algorithms I think have been discovered. The problem is I think almost all my colleagues have worked. Rich Vuduk worked on this, Adipanar worked on this thing, and I think we teach this thing every year. If you kind of follow a traveling salesman order in the sparse matrix, I think that's really great, for example, but good luck computing that efficiently. So that will minimize cache misses. The reality there is, the high-level reality is, let's say you reorder to the perfect possible order. that will minimize any cache miss in the dense vector. You still need to stream the sparse matrix completely, and then you can build this thing called the Roofline Model, which is if accesses to the vector was free, meaning I eliminated all the cache misses to the vector, how fast can I go? Just by going over the non-zeros of the sparse matrix. And then create a performance upper bound, which is my colleague Sam Williams does this called rooflines. And you'll see that most of the time you're 85% there anyway. So you're fighting for 15% performance with this reordering. There's not much juice to squeeze, so to speak. And then that encouraged, again, my colleagues, Jim Demo and his students to think about what can we do outside sparse matrix dense vectors, because there's not much we can do here. Clearly, the ceiling is obvious. And they said, well, if I have an iterative solver, can I communicate every S steps as opposed to every step? So that created the rediscovery of a lot of algorithms called S-step methods. And there's lots of cool research there that I haven't been involved, but mostly for numerical methods like Krylov solvers and so on. So the reality is reordering is a cool area of research, but gains are somewhat limited. Maybe for dense matrix. Actually, you give me an idea. For the things that I talked about, like sparse matrix times tall skinny dense matrix, now the potential gains are higher because you're doing it on a dense matrix, the accesses are more expensive, and you're doing it many, many times because you do it for each layer, for each epoch. So maybe it's time to revisit those algorithms and see even that 15% might be very important when you do it many, many times. So
all right.
It's a good point. That was the easy question?
Yeah, that was the easy question. It was a preparation for the next one. Okay, so in this community, we are quite familiar with dense computation, either with linear algebra, polynomial algebra, and also some of us do sparse. But we don't have the same, of course, experience as people in your community, so that's why we were so happy to have you here. So for dense computations, let's say dense linear algebra or dense polynomial algebra, if I want to have a sense of how far I can go with my implementation, I have different complexity measures. Of course, I have the work or algebraic complexity. I can estimate the span, the cache complexity, and if I know the architecture I'm targeting with these measures, with my experience, that can tell me something why I can expect this speed up here and maybe not linear speed up with that particular problem. But this is maybe because the dense case is easier to analyze theoretically. So in the sparse case, so do you have theoretical model, maybe with some assumptions that can help you estimating what you can expect on that particular architecture?
Yes. I actually have an unanswered question in my mailbox because I was busy writing proposals and I postponed. Someone asked me exactly that. What is a roofline? This is the same thing that I was telling you for sparse computations. I want to do a research on this. I said, some of it exists. So let's start with theoretically. Theoretically, it depends really on the problem, right? If you are doing iterative solvers, it's pretty easy to quantify the bounds. Number of non-zeros times is the time that it takes to do one SPMV. And you can quantify empirically using a simple roofline that says the best I can do is have no cache misses beyond the initial phase of I need to load the vector once anyway. And then you can get pretty close bounds. When you go to complex sparse codes like direct solvers, sparse direct solvers, you have to, both the complexity and empirical one becomes hopeless. So what people do is they take a model problem, let's say 5-point stencil, 7-point stencil, like a 2D or 3D mesh connectivity, and say, this algorithm runs on this time on 3D connected grid. This algorithm runs, but in reality, your mileage might vary because almost nothing is a grid. But what can you do if you can't, come up with a model? In sparse computation, in sparse matrix multiply, for example, we had to take, let's assume random distribution of non-zeros, and then you do some probabilistic bound, simply because nothing else seemed to be analyzable meaningfully. So those are the issues. I would say in many cases, we do try to get a roofline, empirical roofline bound than an irrelevant complexity bound on a matrix that almost never exists. But if you can say, know the structure of the problem, that's the best case. Like, if you can say, this matrix is D-regular, it's like D non-zeros per column, always perfect, then you can come up with tight bounds. But if it's like, it can be any structure, yeah, it's hard to say anything about that at that point, I think. Yeah, even if something loses, this is a sparse matrix with degrees distributed in power law. That takes more sophisticated math, but you can say stuff like how much work it's going to take. But with no assumptions, then you're unfortunately going to go into a place that I really hate, which some people go, which says, in the worst case, the output will be dense, so our algorithm is optimal. No, your algorithm is not optimal. So I would recommend, there is okay, this is actually, I'm going to take one more minute. I think I like the definition of flops, which is, sparse flops is the absolute minimum number of intermediate products you have to do, Aij, Bj, K kind of stuff. Or it doesn't need to be. In this case, it's just for sparse matrix. But if you were solving a system of linear equations, again, there would be scalar multiplications you have to do where both operands are non-zero. Okay, so that's the minimum number of operations you have to do for that input, right? And this is input dependent, but you can come up with algorithms that says it runs on flops time, meaning it doesn't do anything more than what is absolutely necessary for any input you can give. Now, these algorithms are hard. There's always going to be some time to read the input. But if reading the input kind of stuff is asymptotically smaller than the flops, then you can say this algorithm is for every input optimal. And that would be the best thing. And there are some algorithms for that. Like sparse matrix multiply has that algorithm. Direct solvers have that algorithm. I think the title was partial pivoting in time proportional to number of arithmetic operations. So those kind of things would be perfect. And I hope people don't stop with saying the output can be dense. So my algorithm is optimal, I'm done, and move on to discover more tight bounds. That's all I can say.
Wonderful. Now you really deserve your beer, and everyone does. Thank you so much for this wonderful tutorial.
Thank you. I would say everybody deserves their beer.
If I may, yes. So thank you for coming. The reception is officially at 7 o'clock, but it might be a bit later than 7 o'clock. So expect more 7 past 15. Okay? But just a small delay. And it's here in the hall.